In this video, we're going to go over science paper 1 for the year 2016, and this paper was written by the GCE candidates. So let's have the question 1. Figure 1.1 shows an experiment which was carried out to measure the time interval of a simple pendulum. So we have the diagram of a simple pendulum and some positions. So the initial position is point B. Then the bulb was put to point A and allowed it to flow freely. So if this one is allowed to go freely, it is going to oscillate. It is going to move back and forth. So the question is, the bulb was oscillating between A and C. State the meaning of the term oscillation. So we'll say moving or swinging back and forth. Back and forth. Then we move on to question B. So under question B, if the pendulum bob took 0.20 seconds to swing from point A to C, calculate the period. So the concept is, if we move from point A up to C, then what is the value of n, which is the number of oscillations? So the number of oscillations is 1/4 plus another 1/4, because from A to B is 1/4, B to C is 1/4. So if we add, we get the lowest common denominator, which is 4 into 4 is 1 times 1 is 1. 4 into 4, 1 times 1 is 1, which is the same as the half. Or you can just commit that point to memory. Whenever it moves from point A to C is half. So the number of oscillation is half, which is 0.5. Now the formula for period, we begin with a symbol which is capital letter T, is given by small letter t, time taken, divided by the number of oscillations. So time is 0.20 seconds, then divided by number of oscillations is 0.5. So say 0.20 divided by 0.5, I'm getting 0.4 then seconds. So it means that for one complete oscillations to be made, the number of seconds taken should be 0.4. And it's making sense if you can look at our diagram here. For us to make one complete oscillation, the bulb must move from A to C and back to A. Now remember, A to C is getting or is taking 0.2 seconds, then another 0.2 seconds. So to complete one oscillation is 0.2 plus 0.2, giving us 0.4 seconds. Then our question C is, using your answer to 1B, determine the frequency of the bulb. So symbol for frequency is small letter f, given by 1/period, which is, we have 1 divided by 0.4. So 1 divided by 0.4 is giving me 2.5 Hz. So this is our final answer. Or if you want, we can find the same formula, the same answer for frequency, but we are just going to use the reciprocal of the formula for period, which is, instead of writing 2/n, we write n/t. So number of oscillation is 0.5 over then the number of oscillation, the time is 0.2. So if you divide 0.5 divided by 0.2, I'm getting the same answer, 2.5 Hz. Now if you look at the frequency is just defined as the number of complete oscillations that are made in 1 second. So 2.5 oscillations are made in a given second. Remember, for period, the definition for period is the time taken to make one complete oscillation. while the definition for frequency is the number of oscillations made in 1 second. So 2.5 Hz made in 1 second. We move on to question 2. A lion of mass 200 kilograms is transferred from the moon to the earth. Acceleration of free fall on the moon is 1.67 meters per second squared, while that on earth is 10 meters per second squared. Question A state the first one, an instrument commonly used in the laboratory for measuring the amount of material. So whenever you are told the amount of material in a body, this is same as the instrument that you can use to measure mass. So under a laboratory, we can use a beam balance, and in most cases that should be electronic beam balance. Then we move on to question 2. So question 2 is state a mass of 200 kilograms lion on earth. So this 200 kilograms is the mass of the lion on moon. Now we want to look at what is its mass if that lion is taken to the earth. So the mass is still 200 kilograms. Why? Because mass is constant, so mass doesn't change. Then for B, calculate the weight of the lion on earth. So weight is given by the product of mass and gravity. Remember, the mass is 200 kilograms. Gravity is 10, which is our final answer, is 2000 newtons. Question 3a. What is meant by the moment of a force about a P point? So say this is the turning effect. Okay, then B, moment of a force about a point depends on two factors. What are they? So it's force and distance, which is, we can just say, perpendicular distance to the pivot. Now we have question C. Figure 3.1 shows a uniform meter rule which is pivoted at the 20 centimeter mark and balanced horizontally by an object of 3.15 newtons placed at the 10 centimeters mark. So we need to use the principle of moment, where we are saying moment 1 must be equal to moment 2 for this to balance. Then we need to identify the pivot, but in our case we have the pivot, so this is the pivot because it's where this can turn. Then we have the point of action. So the point of action is the point where the force is, in our case where our 3.15 newton is, so point of action. Now whenever you are getting the distance, you get a distance from the pivot up to the point of action, so this is our distance 1. Now for the other side, we need to find a point where the mass must be concentrated. In our case, the question is calculate the weight of the meter rule. So for this meter rule, we need to look at where the center of mass is, where the entire mass of this meter rule is concentrated. Now weight. So how can we find this? So we need to look at since this meter rule is a uniform meter rule, meaning at 50 centimeters is where we are going to consider the center of gravity, in our case the center of mass, since mass is related with weight. So we'll consider this one as our force 2. Then we'll consider this one as distance 2. So let's say we know that moment 1 must be equal to moment 2 for this to balance. Then in our case, we'll say force 1 times distance 1 is equal to force 2 multiplied by distance 2. Force 1 is 3.15 newtons multiplied by distance 1. The distance from this 10 up to 20 is 10 centimeters. Then force 2 is what we are solving for, so we just say force 2 times distance 2. The distance from 20 up to 50, so it's just the difference. 50 minus 20 is 30 centimeters. Then we can do math. 3.15 times 10 is 31.5 Newton centimeters is equal to 30 centimeters F2. So we divide by 30, even here by 30. So that if we cancel, we get our F2 is equal to centimeter cancel. So we've got 31.5 divided by 30. So I'm getting my final answer as 1.05 newtons. So this is the weight. If what we can check if our answer is making sense. So let's say moment 1 is equal to force times distance. So the force is 3.15 times 10, which is 31.5 Newton centimeters. Now let's check for moment 2. Is force times distance also. The force is 1.05 times the distance, remember, 30. So 1.05 times 30, I'm getting 31.5. Okay, so we can see that these two moments are equal. Therefore, we can conclude that our setup is in equilibrium. Okay, we move on to question 4. Figure 4.1 shows a stone of mass 2 kilograms which drops from the top of a cliff and takes 2 seconds to strike the ground. Acceleration or free fall g is equal to 10 meters per second squared. Now we have question A. Name the form of energy possessed by the stone before it falls. So before it falls, here we'll say it was at rest, and whenever it is at rest and there is a certain distance which is height covered, that energy is called potential energy. Then the other question is determine the height of the cliff. So how can we find the height? So we are going to use the equation of motion. So the first equation is v is equal to u plus at. The second one is s is equal to u plus v over 2 times t. Then the third one, s is equal to ut plus half at squared. The fourth one, v squared is equal to u squared plus 2as. Now we know that v is final velocity, u initial velocity, a acceleration, t time, then s is the displacement or distance. So in our height, in our case, the s represents the height that we are looking for. Now we need to look at the data that we have so that we are able to choose the formula that will suit the data. So let's collect the data. So say SUVAT is the best way to remember. So s is the distance, so we don't have, we just put a question mark. U is the initial. Now whenever you drop something, as long as there is this word of drops, remember there is a difference between dropping and throwing. So whenever the language of drops is mentioned, the initial is always 0. Then what else? Final velocity, we don't have the speed at which this stone is hitting the ground, so put a question mark. The acceleration, we have this, the acceleration due to gravity, which is 10 meters per second squared. Then time, we have 2 seconds. Now we can see that we need a formula in which we have the S. So we have the third, fourth, even the second one. From there, we need to make sure that the formula that we are choosing must consist of what we want, but it has to make sure that there should no other variable that should be missing. What we mean by that, we can't choose like the fourth one, since the final velocity is not given and our task is we need S. So we can't solve two variables at once. We only need a formula that suits only one variable, the one that we are solving. So we can see that this equation is suiting the data that we have, because initially we have T, acceleration to gravity, we have. Now let's see if we can summarize our formula. So we know that S is equal to ut plus half at squared. Now whenever you are looking at a free fall object, we know that the initial is always 0. So let's substitute 0 times t plus half at squared. So this one must be cancelled. Now where there is S, I'm going to substitute with height. Then we have half. Then A, I'm going to substitute with gravity, which is the acceleration due to gravity, G, then T squared. So this is the simplified formula that I think you should commit to memory whenever you are dealing with finding the height, as long as you are dealing with the free fall. We can now find our final answer. So height is equal to half, then the gravity is 10, time is 2 seconds. So if we do math, so we are squaring, so if we do mass, I mean multiplication math here, we do 2 into 2 is 1, 2 into 10 is 5 times 2 times 2, which is 4. 4 times 5 will give us 20 meters. So the height of our cliff was 20 meters. So that's our final answer. Then for question C, calculate Roman number the kinetic energy of the stone when halfway down. The formula for kinetic energy is Ki is equal to half mv squared. Now we can't find the kinetic energy since we are not given the velocity. So what are we supposed to do? So what we are going to do is we are going to find the potential energy before the stone started to fall down. So potential energy, which is P, is equal to mass gravity times height. Remember, the mass is 2 kg, gravity is 10, the height is this number that we found here, which is 20. So if you do the math, you get 400 joules. So at this point where we are considering to be at rest position, the potential is 400. Now the question is, as this stone is falling down, what was happening to the potential energy? So the potential energy started to be converted into kinetic energy, because we know that the kinetic energy is a type of energy possessed by an object that is in motion. So since the potential energy cannot be stored in something that is moving, so the potential energy that we had before the falling down, it must be converted into kinetic so that it suits the motion. Now we want to look at the potential energy, how much from that 400 will be converted when it moves halfway. So the halfway is after it covered a distance of 10 meters. So at this point, the potential energy must be equal to kinetic energy. In our case, this 400, half of it must be converted into kinetic, which is 200. So at this point, when it moves the halfway, the kinetic energy must be equal to 200. So that is our concept here. So we have 200 as our final answer. Then for Roman number 2, the final velocity of the stone as it strikes the ground. As it strikes the ground. So what are we going to do to find our final answer? So we know that we have the formula for this kinetic energy. So we want the velocity, which is the speed. Now, do we have the kinetic energy upon reaching the ground? Yes, we do. So at this point, you need to remember that all the potential energy that we had at the beginning has converted into the kinetic. So that 400 is the total at this point. So there are two ways in which we can handle this question. We can say kinetic energy is equal to half v squared, which is we have 400 times half. Then remember the mass is 2 v squared, so we can cancel this, which is v squared is equal to 400. Then we take the square root also here. So the velocity upon reaching is 20 meters per second. Okay, so that is or if you want, we can just summarize the formula. So how can we summarize this formula? So let's say we are saying the potential energy, the value of the original potential energy at first must be all converted into kinetic at the point of reaching the ground. So say PE is equal to KE. So PE is mgh. Then the formula for KE half mv squared. So what I just want here is I want to equate the two formulae. Now we can see that we can cancel the mass here, which is same as mass divided by mass. Then we have gh is equal to half v squared. So we can cross multiply, or we can multiply by 2. So 2 times this one will give us 2gh. Then 2 times this one, these two will cancel, which is giving us v squared. Then we can introduce the square root, also the square root, which is, I just want to give you the formula. Final velocity is equal to 2gh. So this is the formula that you can use whenever you're trying to find the velocity, which is the final velocity is equal to, if we do substitution, we have 2 times 10 times the height is 20. If you do the math here, you get 400, the square root of 400, you still get 20 meters per second. Do we have another way in which we can find the final velocity? Let's go back to our data. Do we have another way in which we can find Yes, we do. We can still find the velocity, the final velocity, if we use this formula, the above formula. So say velocity is equal to u plus at. So final velocity is equal to, our u is our initial 0 plus the acceleration is 10, then the time is 2. So 0 plus 10 times 2 is 20. 20 plus 0 is 20 meters per second. So we still have the same answer. Okay, we can move on to question 5. 2 metal plates A and B, one with shiny surfaces and the other painted black, are heated to a temperature of 100 degrees Celsius. The metal plates are then placed in open air or insulating materials and allowed to cool. The table below shows the results obtained with time. So time in seconds, temperature of metal plates in degrees Celsius. So at 0, the temperature was 100. After 30 seconds, this one reduces to 92, 85, 60 seconds, 87, 74, 90, 84, 67, 120, 81, 63, 150, 79, 60. So we can see from the numbers that metal B was losing heat fast to the environment compared to metal A. Then we move on to question A. By what process or processes of heat transfer are the metal plates losing heat to the surrounding? So metals, we know that they are in solid state, so here is conduction. Conduction, which metal plate is losing heat faster? Metal B. So say metal plate B. State with a reason which metal plates A or B has shine surface. So say metal plate A. So what I want you to have in mind is that when it comes to absorption or emitting of heat, the one that absorbs heat faster will lose heat faster also. Then the one that takes time to absorb heat will also take time to emit heat. So the speed at which heat is absorbed is the same speed at which heat must be emitted. If heat is absorbed fast, must also be emitted fast. So for the shine one, we know that shiny surfaces reflect. To reflect, we are saying the heat must bounce back. Now, or maybe to summarize our answer, we are saying shiny surfaces or white takes time to absorb heat, but for black is a good absorber. Now, even if it's a good absorber, it is also a good emitter. It emits heat fast. So for this one, for the shine one, it takes time to absorb heat, it also takes time to emit. So reasoning, because it was not emitting heat fast. Okay, we move on to question 6. Figure 6.1 shows a vibrating turning form Y in air. So we have vibrating turning fork air. So whenever you hit a metal or anything, then as long as vibrations are producing, those vibrations will cause sound to be produced, because we know that sound is produced by any vibrating object. So here we are looking at the production of sound. Question A, state the nature of wave produced by the turning fork. So it's longitudinal. So sound is under longitudinal type of wave. So in longitudinal, we are expecting to have refraction and compression. Then be shown diagrammatically the regions created by the wave produced as it passes through the air. So here we just want to draw a longitudinal wave. So under this one, you need to have some of these lines that are compressed. The compression is where these lines are closer to each. Then from there, we need to have where they are spread out. Okay, so these where they are squeezed together is called compression. Then where they are spread out, these are refractions. Then we move on to question C. Explain what happens to the speed of the wave in air if the rate of vibration of y increases but the length of the wave produced remains the same. So remember, the length is giving us the wavelength. So same as whenever the wavelength remains the same but increases the vibration. So will the vibration, the increase in vibration, change the speed? Okay, let's see. So let's look at the formula for speed. So we know that speed, which is velocity, is given by frequency multiplied by lambda, which is wavelength. Now let's look at the frequency. So frequency is defined as number of oscillations or waves made in 1 second. So the vibration, whenever we increase the vibration, we are indirectly increasing what? Frequency. We are increasing we are making a lot of vibrations at once, meaning we are making a lot of waves in 1 second. Okay, if that is the case, let's make some numbers. So let's say our distance is 2 meters. Then at a normal rate of producing this vibration, we are going to say we have 5 hertz. So if we want to find the speed, we know that where there is frequency we put 5, then here we put 2. So this will give us 10 meters per second. Now let's say the wavelength remains the same. Now let's increase the frequency. Let's say the frequency is 20, since we are increasing the vibration. So if we use frequency as 20, then t, which our wavelength remains to here, we get the answer to be 40 meters per second. So from the calculations, we can tell that if the frequency increases, then the speed of that wave also increase. So say the speed of the wave would increase because increase in frequency results in increase in speed. So that's what we can say for this one. Move on to question 7. Under question 7, we have figure 7.1 shows a ray of light entering and leaving a glass block. Okay, the first question, name the rays labeled A to D. So let's begin with A. So A is the one striking the glass block. So this is our incident ray. Then B is the one bending after striking the glass block. So this is our refracted ray. Then we have C. C is the one leaving the glass block back into air. We call this one as the emergent ray. Then D, this one is just the one that bounced. So this is our reflected ray. So the one reflected must just bounce, then the one refracted is about bending. On the diagram, indicate I, which is the angle of incidence, and R, which is the angle of refraction, for angles of incidence and refraction respectively. So we have to identify the normal ray. So the normal ray is always drawn in dotted. So this is our normal ray. So the angle between the incident ray and the normal ray is our angle of incidence. So this is our angle of incidence. Then the angle of refraction is between the normal ray and the refracted ray. So this is our angle of refraction. See, for a certain piece of glass block, the angle of incidence was found to be 25 degrees and the angle of refraction was found to be 16 degrees. Using the information, calculate the refractive index for this piece of glass block to 2 decimal places. So refractive index given by small letter a can be calculated by sine I, which is the ratio between sine I and sine R. So sine I is the angle of incidence, 25 degrees, over R is 16. So with sine 25 divided by sine 16, I'm getting 1.53. So just say 1.53, since we are taught to do decimal places, so we need 2 numbers after the decimal place. Question 8. Figure 8.1 shows a metal plate inside a vertical solenoid above a small piece of nails. So we have the solenoid is just the process under electrical method in which we can make a magnetic material to become a magnet. So we have a metal bar inside the solenoid, then we have some nails placed here. So let's go to the first question. Describe the behavior of the iron nails when the switch above is on for several seconds, then off if the metal is made from. So the first one, we assume that this metal is aluminium. So what will happen? So say nothing will happen to iron nails. Because aluminium is a non-magnetic material. So for aluminium, we know that it cannot be made into a magnet. So nothing, even if you switch on the apparatus or the setup, for we don't care for how long this setup is switched on. So the aluminium, if the metal bar inside the solenoid is aluminium, then nothing will happen because it will not be turned into a magnet. So nothing will happen. Then for iron is a magnetic material, and it's soft magnetic material, meaning it is easy to magnetize. So immediately it is switched on, then this iron, if this metal bar is iron, then it will start making the magnetic field lines. So because of the formation of magnetic field lines, and because iron is easy to magnetize, then these iron nails will be attracted to this point due to the force of attraction. So say iron nails will soon be attracted to the iron bar. So iron nails, so let me say iron nails up here. So iron nails will soon be attracted to the iron bar after the switch is on. And will immediately fall down after the switch is off. After the switch is off. So the concept that we are looking at here is, for iron, we know that it's easy to magnetize. So immediately you switch on, that iron metal is made into a magnet and it is going to attract the iron. Then immediately you switch it off, it will lose its strength via demagnetization, hence the falling down of iron nails into the plastic beaker. Now, what of the steel? The steel is the different case for the iron. For this one, we'll say the iron nails will take time to be attracted. And take time to fall down. So that's what we are expecting. Then the reason is because iron is a hard material, hard magnetic material. What it means by hard is it's hard to magnetize and hard to demagnetize. Or for sometimes you can also maybe find it in textbooks that steel forms the permanent magnet. So sometimes we may have those iron nails remains stuck. Then we move on to the last question. Figure 9.1 shows extremes of alpha. So this is our alpha. We have beta, then gamma. So rays pass through a uniform electric field represented by tracks A, B, and C. Okay, so we have some charges, positive, negative, then neutral. Identify the tracks marked A. So marked A, deflected toward the positive terminal. So if this is deflected toward the positive, its nature must be negative. So A is beta. So A is beta. Then what of B? So let's go back. B didn't deflect to endpoint, so it is neutral, which is gamma. Gamma has no charge. Then C deflected toward the negative, so C must be positive, is alpha. To summarize our answer, beta has a negative charge, gamma has no charge, alpha has a positive charge. What is the charge for the radiation represented by the track marked B? So say neutral. Neutral, or we can just say no charge. Then thorium nucleus undergoes alpha decay by emitting one particle to form a daughter element whose symbol is Rn. Complete the equation above that represents the decay of the thorium, including the nucleon number and proton numbers of the particles concerned. So what happens to the mass number? You subtract 4 units. So 232 minus 4, getting 228. 280 is what we are going to get here. Then the atomic by 2, so this becomes 88. Then plus H for 2. So this is what we can share. So hopefully this video is making sense to you, and if that is the case, you have to hit the like button. Thanks for watching.